The objective of this presentation is to gain insights into the diffusion of gas molecules such as carbon dioxide, methane, hydrogen, nitrogen, water, ethanol in cage-type zeolites such as DDR, Chabasite, LTA, ITQ-29 and TSC. In all cases, the windows separating adjacent cages are 8-ring windows, and the aperture size is in the range of 3.6 angstrom to about 4.1 angstrom. This slide shows the pore landscape of Chabasite. Per unit cell, indicated here, there are 6 cages. The volume of one Chabasite cage is slightly larger than that of DDR zeolite, but significantly smaller than the volume of a single cage of LTA zeolite. Each cage is separated from an adjacent cage by narrow 8-ring windows. Here are the window dimensions. This is 3.8 angstrom in this direction and 4.2 angstrom in this direction. This table provides further structural details such as the dimensions of the unit cell, the framework density, the pore volume, and the surface area. This slide shows the pore landscape of DDR zeolite. Per unit cell, indicated here, there are 12 cages. The volume of each cage is 278 cubic angstrom, which is significantly smaller than the single cage of LTA or ZIF8. Each cage is separated from an adjacent cage by 8-ring windows. This shows the dimensions of the 8-ring windows separating cages. The smallest distance is 3.65 angstrom, and the longest distance is about 4.4 angstrom. Further structural details of DDR zeolite are provided in this table. These are the unit cell dimensions ABC, pore volume, surface area, this slide shows the pore landscape of the all silica version of LTA zeolite. LTA stands for Linde type A, Linde being the name of the corporation that was responsible for its synthesis. Here is the structure of one unit cell. There are 8 cages per unit cell. The volume of one LTA cage is 743 cubic angstrom, that is intermediate in size between a single cage of ZIF8 and Chabasite. Each cage is separated from the adjacent cage by 8-ring windows. The window dimensions of all silica LTA zeolite are shown here: 4.1 angstrom in this direction and 4.5 angstrom in this direction. This table provides further structural details such as the unit cell dimensions, the framework density, the pore volume, and the surface area. This slide shows the structure of ITQ-29, which is an all-silica zeolite. This is one unit cell of ITQ-29 and it contains 1 cage. The volume of one ITQ-29 cage is 678 cubic angstrom, which is intermediate in size between a single cage of zeolite and shabasite. Here are the window dimensions for ITQ-29, 4 angstrom in this direction and 4.2 angstrom in this direction. Further structural details of ITQ-29 are shown on the slide. These are the unit cell dimensions. There's the framework density, pore volume, and surface area. This shows an unit cell of TSC zeolite that is different from the other cage type zeolites that we have considered. There are 2 types of cages. These are the super cages with volume of 2,553 cubic angstrom. Then we have cages that are similar in size to that of LTA zeolite, and the volume of each of these LTA cages is 743 cubic angstrom. The super cage is connected to an LTA cage by 8-ring windows. The super cages are also connected to pockets, and the pockets super cage connection is via 8-ring windows shown here. Here is another view of the unit cell of TSC zeolite, focusing on the windows. The super cages are connected to LTA cages by 4 angstrom to 4.2 angstrom size 8-ring windows shown here. The super cages are also connected to small pockets through 8-ring windows that are 3.1 angstrom times 5.4 angstrom in size. These pockets are not that important because their capacity to host molecules is very, very insignificant in compared to the storage capacity within the LTA cage and the super cage. And therefore, these window dimensions shown here is not too relevant. The relevant window size is this one, shown here. This slide shows the precise window dimensions for the 2 types of windows that are present in TSC zeolite. The 8-ring windows connecting the super cages to the LTA cages have sizes ranging from 4 angstrom to 4.2 angstrom. The 8-ring windows connecting super cages to pockets are oblong in shape, and the narrowest dimension is about 3.1 angstrom. Due to the narrow constriction, it's likely that these windows do not allow any gas molecules to occupy the side pockets because of the severe restriction to molecular motions. So this window is irrelevant, and the storage capacity of gas molecules inside the pockets is very, very limited. Further structural details of TSC zeolite are provided in this table, including surface area, pore volume, unit cell dimensions. These unit cell dimensions are significantly larger than the unit cell dimensions for LTA, zeolite, and chabazite. This slide compares the window dimensions for cage type zeolites. We will see later that the minimum size of the window aperture in each case is relevant when comparing the diffusivities of guest molecules inside these structures. We should therefore expect that the diffusivities in DDR, which has the narrowest dimension of 3.65, to be lower than the diffusivity of the same guest molecule in chabazite, and the diffusivity of that guest molecule would be larger in, say, LTA all silica zeolite. Small differences in the window aperture will make a large difference in the values of the diffusivities, and these differences could be about 1 to 2 orders of magnitude. This slide compares the cage sizes of DDR, chabazite, ITQ-29 and LTA zeolites. DDR has the smallest cage volume. The cage volume of chabazite is slightly larger. ITQ cage is larger than that of chabazite, but slightly smaller than that of LTA all silica zeolite. The frameworks of cage type zeolites, chabazite and LTA are not rigid, but subject to flexibility, as indicated in these animations shown here for chabazite and LTA. For further details on the influence of framework flexibility on diffusivities, you may consult this reference. Here are animations showing the framework flexibility of ITQ-29. This is the framework without any guest molecules, and this is the ITQ-29 framework containing 1 molecule per unit cell of methane. These are the windows connecting the 2 adjacent cages. Windows here, 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 and here. In each cage, each frame, we see methane trying to hop across the windows. This slide shows the intercage hopping of methane in ITQ-29, LTA all silica, and DDR. Let's look at the animations, and you can see clearly in ITQ-29 the intercage hopping of methane molecules. here, 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 here you can see this is for LTA. You can also observe the intercage hopping of methane. Here, here it has crossed the cage. The window dimensions of these two zeolites are larger than for DDR, and for DDR the diffusivity of methane is considerably lower than that for LTA and ITQ, and that is evidenced by the fact that most of the hopping occurs within the cage. And in this case, we track the trajectory of one methane molecule, and the trajectory is indicated by these blue lines. And up to this time, the methane molecule has not crossed the windows to any of the adjacent cages. And if we watch this window patiently, we will see one hop occurring to this window. Let's wait. Note that we are just tracking one methane molecule that was initially located here, and now it has entered this cage because the trajectory has entered the adjacent cage. So this intercage hopping occurs much less frequently than in these two types of zeolites. This slide summarizes the molecular dynamic simulation data for the self-diffusivities of methane in different cage type zeolites. The hierarchy of the diffusivities is dictated by the size of the window aperture. In each case, we use the d-min, which is the minimum dimension of the window aperture, to characterize the window size of that particular zeolite. For example, the red circles show the self-diffusivity data for LTA all-silica zeolite, which has a d-min value of 4.1 angstrom, and the inverted pink triangles show the self-diffusivity data for DDR, whose value of d-min is 3.65 angstrom. Note that the differences in the diffusivity values are about 2 orders of magnitude between LTA and DDR. Now, the diffusivity values are also a function of the concentration of the methane guest molecules inside the pores, expressed in kilomoles per cubic meter. For a comparison of the diffusivity values, we take the diffusivities at a loading of 1 kilomole per cubic meter, and that diffusivity values for these cage type zeolites is plotted as a function of the window dimension d-min, and we see that the self-diffusivity values at this loading correlates with d-min value, ranging from 3.65 to 4.1 angstrom, and the variation is about 2 orders of magnitude. So by appropriate choice of the cage type zeolite, we can manipulate the selectivity values for mixture diffusion. Let's examine the intercage hopping of carbon dioxide in DDR zeolite. Carbon dioxide is a pencil-shaped molecule, and the minimum cross-sectional dimension is 3.1 angstrom, and the only way CO2 can hop across the DDR window is in a lengthwise direction. So we will see animations of the intercage hopping of CO2 in DDR. And before we do that, let me say that we are going to track the trajectory of one of these CO2 molecules as it hops or attempts to hop from cage to cage. Let's start the animation. At the moment, it has only hopped within the cage, and there it has crossed the window and has approached and entered this cage, as you can see from the trajectories. It's attempting to cross this window, but it has returned to this cage. And now it's that same molecule is trying to cross this window and has not been successful so far and has returned to this cage. Then the net result is that the CO2 molecule that was tracked started in this cage, entered this cage, and spent all its time trying to hop to this cage unsuccessfully, and the attempt to hop across the window to this cage was also unsuccessful, and all the trajectories for CO2 are to be found within this cage. So for the duration in which that CO2 molecule was tracked, it underwent intercage hopping successfully only once. Let's examine CO2 CH4 mixture diffusion in case type zeolites, chabazite, DDR, and LTA. Let's first have a look at the animations for chabazite. This CO2 molecule is attempting to enter this cage, but is hovering around the window site. This is for DDR. You can see the preferential perching of CO2 at the window regions. It stays at the window regions for a considerable amount of time before entering either of the adjacent cages. Intercage hopping of CO2 is much easier in LTA zeolite because the window dimensions are larger. Here you can see a CO2 molecule hovering around the window site. Molecular dynamics simulations for the diffusion selectivities for CO2 CH4 mixtures are plotted here as a function of the total pore concentration expressed in kilomoles per cubic meter. The diffusion selectivities for each of these four cage type zeolites decreases with increasing pore concentrations. The hierarchy of diffusion selectivities is dictated by the window apertures. DDR has the highest value for CO2 CH4 selectivities because it has the smallest aperture size of 3.65 angstrom. The red circles show the selectivity values for all silica LTA, and these values are the lowest because the window dimensions of 4.1 angstrom in this case is significantly larger than the minimum dimension of 3.65 for DDR. For a pore concentration of 15 kilomole per cubic meter, the diffusion selectivity values are plotted against the window dimension d min, and we can see a reasonable correlation between the diffusion selectivities and the window dimensions for these four cage type zeolites. The selectivity for DDR is about 1 order of magnitude larger than for all silica LTA zeolite. The company called NGK Insulators in Japan offer membrane modules which have a monolithic structure, and the inner walls of the tubes are coated with a thin layer, typically about 20 micrometers in size, this layer, and this layer consists of DDR zeolite that allows selective CO2 permeation from a CO2 methane mixture. Let's look at animations showing the diffusion of mixtures of methane and hydrogen in chabazite and LTA zeolites. Hydrogen is a significantly smaller molecule and can undergo intercage hopping more easily than its partner methane. The hydrogen is shown by the white spheres, and it has crossed this window rapidly into the adjoining cage. This slide summarizes the MD data on hydrogen methane diffusion selectivities in 4 different cage type zeolites. The MD data for the diffusion selectivities at a loading of 15 kilomoles per cubic meter are plotted against the window dimensions in this graph. The diffusion selectivities correlate well with the value of d min, which represents the smallest window aperture for these 4 cage type structures. The highest hydrogen methane diffusivity is realized with a Chabasite, and the smallest hydrogen methane diffusion selectivity is obtained with all silica LTA zeolite. This slide shows animations for CO2 hydrogen mixture diffusion in Chabasite, DDR, and LTA zeolites. As expected, hydrogen undergoes intercage hopping much more easily than carbon dioxide. It has already crossed this window twice. The hydrogen shown by the white spheres has undergone intercage hopping here. For LTA, hydrogen has crossed the window. CO2 is hovering around the window region, not quite entering either of the cages. It also effectively blocks the intercage hopping of hydrogen. Let us examine the intercage hopping of 2 pencil-shaped molecules, carbon dioxide and nitrogen, in LTA all silica zeolite. Also in this case, you note that carbon dioxide that is most strongly adsorbed is firmly perched at the window regions and has a tendency to prevent the intercage hopping of nitrogen molecules. This has the effect of increasing the selectivity of CO2 with respect to nitrogen, because nitrogen is being prevented from hopping across the windows due to the strongly adsorbed CO2 that prefers to occupy the window sites. For diffusion of water in LTA, there's strong hydrogen bonding between pairs of water molecules that has the net effect of reducing the mobility of water, and the intercage motion of water molecules is severely retarded due to molecular clustering. This is qualitatively explained by this animation, where you get a feel for the molecular clustering phenomena. Molecular clustering also occurs for pairs of methanol molecules. For water-methanol mixtures, there is significant hydrogen bonding between water molecules and water-methanol molecules. The bonding between water-methanol molecule pairs leads to the phenomena called mutual slowing down. Let's first have a look at the animations here. The green molecules are water. The phenomena of mutual slowing down is quantified in this diagram, which plots the self-diffusivity of water, shown by the blue triangles, and methanol as a function of the mole fraction of water in the adsorbed phase, where the total pore concentration of the mixture is kept at the value of 50 molecules per unit cell. With increasing water loading, the methanol self-diffusivity undergoes a reduction. Also, concomitantly, the diffusivity of water is reduced with increased concentration of methanol in the mixture. Both components undergo slowing down effects. Let's examine the influence of molecular clustering on diffusion in DDR zeolite. We first have a look at the animations for water diffusion in DDR. There's some visual evidence of clustering between pairs of water molecules. There's also some clustering between pairs of methanol molecules and pairs of ethanol molecules, as evidenced here. This graph shows MD data for the self-diffusivities of water, indicated by the blue triangles, and methanol, indicated by the yellow diamonds, in DDR zeolite. Due to hydrogen bonding between water and methanol, we have mutual slowing down of water and methanol. For example, the diffusivity of methanol is reduced by 1 order of magnitude with increased proportion of water in the adsorbed phase. Concomitantly, the self-diffusivity of water is reduced with increasing proportion of methanol in the adsorbed phase. Let's examine molecular clustering effects in chabazite. These animations are for methanol-ethanol mixtures, and there's some visual evidence of molecular cluster formation, albeit qualitative in nature. This graph presents MD data for self-diffusivities in water-methanol mixtures in chabazite. The total loading of the mixture is held constant at 2 molecules per kg, and the self-diffusivities of water and methanol are plotted against the mole fraction of water in the adsorbed phase. We note here the data for self-diffusivities of methanol, indicated by the yellow diamonds, that the self-diffusivity of methanol is reduced due to increased proportion of water in the adsorbed phase. At the same time, the self-diffusivity of water is reduced due to increased proportion of methanol in the adsorbed phase. In industrial practice, LTA is used in its cation exchange forms. LTA4A zeolite contains 96 sodium cations per unit cell, and the location of these cations is indicated by the blue spheres. Particularly noteworthy are these sodium cations that appear to partially block the window regions. This partial blocking of the window regions has a significant influence on the intercage hopping of gas molecules from one cage to the adjoining cage. LTA5A zeolite contains 32 sodium cations and 32 calcium cations per unit cell. The location of these cations is shown here. The blue spheres are the sodium cations and the red spheres are the calcium cations. The window regions are devoid of any cations, and therefore there is a significant difference in the diffusivities of any gas molecules in LTA4A zeolite and in 5A zeolite. In 4A zeolite, the diffusivities are significantly lower, often by 1 to 2 orders of magnitude. Here we see the motion of methane within the cages of LTA4A zeolite. The blue spheres are the cations, and the cations are to be found in the window regions, as you can see. And due to the presence of the cations of the window region, the intercage hopping of methane is hindered significantly. Whereas in 5A zeolite, the window regions are devoid of cations, and this does not prevent the entry and crossing of the windows by methane molecules shown in green. Therefore, whether we use 4A or 5A zeolite, the diffusivities would be significantly lowered in 4A than in 5A. This strategy can be exploited to achieve. Let us examine separations of nitrogen and oxygen using cation exchanged LTA4A zeolites and LTA5A zeolites. Nitrogen and oxygen have similar polarizabilities and magnetic susceptibilities. Nitrogen adsorbs more strongly than oxygen because its quadrupole moment is 4 times larger in both 4A and 5A zeolites. Let's examine separation of a mixture of nitrogen and oxygen in a fixed bed of 5A zeolite. The ratio of the diffusivity of oxygen to nitrogen is 2 because the oxygen has a smaller cross-sectional dimension. The separation is governed by differences in adsorption strengths, and since nitrogen is more strongly adsorbed, the gas mixture exiting the fixed bed in the early stages of transient operation is purified oxygen that is more poorly adsorbed within the pores of 5A zeolite. The situation is different in a fixed bed packed with LTA4A zeolite, in which the windows separating the cages are partially blocked by the sodium cations. This partial blocking of the windows enhances the diffusion selectivity in favor of oxygen, and the ratio of diffusivity of oxygen to that of nitrogen is 100. The net result is that the differences in the intracrystalline diffusivities serve to override the adsorption selectivity advantage that is in favor of oxygen, and the pores are richer in oxygen that has the higher diffusivity value, and the separation is diffusion driven. The gas mixture exiting the fixed bed packed with LTA4A zeolite is richer in purified nitrogen in the early stages of the transient operation. Let's consider the technologically important problem of purification of natural gas. In many natural gas reserves, especially in remote locations, the nitrogen content can range up to 20%. The presence of nitrogen lowers the heating value of natural gas, and therefore for transportation purposes and supply to households, the pipeline specifications demand that the content of nitrogen be less than 3%. One technological solution is to use pressure swing adsorption technology with a suitable adsorbent that selectively takes up nitrogen and rejects methane, the major component of natural gas, into the gas phase so that it can be collected during the early stages of transient fixed bed operation and incorporated into the gas transportation pipelines. Most known adsorbents are selective to methane because of the higher polarizability of methane in comparison to that of nitrogen. Therefore, one technological solution is to use LTA4A zeolite with 96 sodium cations per unit cell. Due to the partial blocking of the windows with the sodium cations, the intercage hopping of methane is severely restricted. Nitrogen, on the other hand, being a pencil-shaped molecule with a smaller cross-sectional dimension, is able to hop across the windows from one cage to the adjacent cage much more easily than methane. The ratio of the diffusivities of nitrogen to that of methane is a factor 25. This is large enough to override the adsorption selectivity that favors methane. Let's have a look at the animation of methane moving across the windows from one cage to the adjacent cage. This is nitrogen hopping lengthwise across the windows. Let's demonstrate the suitability of using LTA4A zeolite for kinetically driven separations of nitrogen-methane mixtures. We consider the experimental data published by Habgood in 1958 for transient uptake of nitrogen and methane in 4A zeolite at 194 Kelvin from a 50-50 bulk gas mixture. The transient uptake of nitrogen, shown by the red circles, shows an overshoot in the loading before it finally reduces in value to 1.2 moles per kilogram. That is the component loading in equilibrium with the bulk gas phase mixture. The uptake of methane, shown by the green squares, is monotonous, and it increases in value to 2.25 moles per kilogram, that is in equilibrium with the bulk gas mixture. During the initial stages of the transient uptake, the pores are significantly richer in nitrogen that has the higher diffusivity than methane. The fixed bed packed with 4A zeolite in a pressure swing adsorber is operated in a transient manner with absorption and desorption cycles. The cycle times can be adjusted to be short enough such that the adsorbed phase is richer in nitrogen, and the more poorly adsorbed methane is rejected into the gas phase and recovered at the exit of the fixed bed adsorber. Here is a list of references for further background reading on diffusivities and diffusion selectivities.